So welcome
Okay,
again to the next session. Next, we have Younghoon Kim from Cornell, who will be speaking to us about latent Gaussian dynamic factor modeling and forecasting for high-dimensional count time series. Younghoon, the floor is yours.
okay, thank you. Thank you for introducing me. And then thank you for giving me opportunity to give the presentation here. So I'm a postdoc at Cornell University, but this is the one of the projects during my PhD thesis. So at UNC Chapel Hill. So this work is a collaboration with my long-term collaborator, Mari Duker and Zach Fisher, and with my PhD advisor, Vladas Piperas. Okay, so here's the motivation in the univariate case. So suppose that you have the latent but stationary Gaussian process with mean zero and univariance. So let's say you can come up with the latent AR1 models. So to make the variance of the ZTs to be one, so you can come up with this type of structure. Okay. In addition to the ZT, you have, let's say you have the XT, which is observable count time series, or it could be any distribution you like. Like, for example, it could be the ordinal distribution, like categorical distribution, which is covered in this paper. So how does the X and Z are connected? So by using the by using the defined G function. G function is a convolution of the inverse CDF of the marginal distribution F, and as it defined as a standard the normal CDF. Okay, so let me give you the two examples. So for example, if the CDF is a Bernoulli, then one has the xt is equal to in this manner. So it could be just defined as the indicator function. So if the CDF of the z values are exceeds some threshold defined by the marginal parameter p, then it could give you 1, otherwise 0. Likewise for the Poisson marginal distributions with the parameter lambda. So you can just count how the z is lies on which the beans, let's say. Okay, of course, the bean is just defined by the cumulative distributions. So similarly, for the other type of the distributions can be defined. So in this the work, we considered the Bernoulli Poisson and categorical and the negative binomial distributions. Okay. So here is the time plots of the illustration. So suppose that we have the AR of order 1, the ZT, which is the black line here. So I'm just introducing the two different the marginal parameters, the blue one and the pink one. And of course, for the Bernoulli distributions and Poisson distributions. For the same, the AR1 process, depending on what distribution you take or what the parameters you take, then the observation series will be determined, and they are giving the different result observations. So suppose that the AR process is non-observable, but we have only this value. Can one get the same characteristics of the AR that you can come up with? So that's the question of this type of model. But we are extending this idea to the high dimensional or multivariate settings with the dynamic vector models, which we'll describe later. Okay, so before jumping to the multivariate extension, so I just wanted to highlight the two things. So as I said, any different marginal distributions can be considered, and this distributions need not be zero inflated. So that's the one good thing. The other good thing here is, I don't know if you are familiar with the discrete value time series. So one of the big concerns so far was how to impose a negative autocorrelations on the X values. But this is very flexible to give the negative correlations of the XTs. We'll see later. So let's go to the multivariate setting of the main interest of this paper. So I have the same structure, but the connections between the ZTs and XTs are marginally defined. Like, for example, this is the same equation that you see in the univariate case, but let's just put the I here. I is the variables. Okay, so D is accordingly the number of the variables of the interest. And the ZT is now follows the dynamic vector, the models, which is defined like this. So my lambda is a loadings matrix, and here is the epsilon. Epsilon t is on the IID noise following the normal distribution, and of course it's independent of the y. So y here is a causal stationary vector, low dimensional vector autoregraph model of order p. Okay. So combining these 3 and 4 equations, we can define the static form of the dynamic vector models. So how one can get the characteristics of the ZTs, the latent ZTs, by using the link functions. So we are calling it second order properties. So second order properties means just simply think it's autocorrelation or autocovariance if it has the univariance. So these autocorrelation functions of the XTs and ZTs are linked through the link function. So link function is entry-wise defined. I'm just using the LIJ. Here, the LIJ is marginally defined by using from the CDFs of the ith and jth variables. Okay, so I'm using here the Hermite expansions of um, my CDFs, sorry, the autocorrelations of the ZTs. Okay, so I'm using this notation here, and this is the standardized of the coefficient um, of the link functions, and each link functions are defined the pairs of the Hermite coefficients, and this is defined like this. So up to some, so theoretically it's up to it's an infinite sum, but as we'll see on the estimation part, it will be truncated by the height, the order of the polynomials. Okay, so how one can estimate this model? So first of all, we need to estimate the marginal parameters of the theta I. So it's quite simple. Just think of each the variable as it is, and we can just use the maximum likelihood of the xits marginally. Okay, and once we just do that, and let's assume we have the estimated link function and its inverse, which we'll cover later. Then, by using the relations of the autocorrelation functions, one can recover the covariance matrix of disease up to the leg order P. Okay. And then just like the standard dynamic vector models, we can just use the PCA approach with the suitable the identifiability conditions. And for the recovering the low rank the var models, we can just use the U-Walker equations. The remaining question here is how to get these the link functions and its inverse. So as I said, the Hermite coefficients are marginally characterized by theta. So let's say we have the theta. Okay. So this estimated theta will give you the estimated link functions, okay, in this manner. And then just think about the grid of the U values, okay, defined within negative and positive one between them. And then just use the pairs and just draw the splines. So here is the illustrations of the link functions and inverse link functions for the Bernoulli distribution and Poisson distributions. So as the parameter gets the evolving, so they will give you the different curve of the link functions and its inverse. And two things that we can see, you can see. So one is the using the splines for getting the estimated in inverse link functions are nearly the identical to its truth. Okay, that's the one thing. And the other thing is, if you look at these Poisson cases, so the red one is the small lambdas, and then lambdas gets larger, and you will see the green lines here. Okay, so note that this, so one is this is the u, the values of the u, and it's the corresponding link functions. So if you can come up with the how the link function is defined, okay, and it almost reached to the ones, but as you can see, it never reaches to the -1. Okay, but this region here is the where the negative correlation should be imposed. So many of the previously defined the discrete value time series are suffering from getting these values, but we are just flexibly use this idea. And this model has been demotivated by the psychometrics approach. So one of the psychometrics people are using, the techniques they used by them is if they are the lambdas in the Poisson distributions are quite large, let's say 10 or over than 10, then they just use the Gaussian approximations. And it supports that idea that the link functions, as the lambdas gets larger, then link function covers the most of the ranges of the -1 to the +1. And then as we just use the dynamic vector models, we have to select the number of the ranks R and the number of the legs P. Okay? Simply just use the cross-validation idea. So let me just walk through the cross-validation for the R. So let's say we have the XTs, and we can just make a block fold, like let's say large B numbers. Okay. For the test data set, let's say, excluding the small bit the block, we can just compute all the things that I just explained before, and then get the values of the estimated parameters. Okay, and then just we can just get these the blocks of the RZs and the estimated the RZs. Okay, and then by the choice of the rank Qs all the way up to, let's say, R max, okay, one can compute the root mean square errors of with respect to um, the the chosen rank, the rank candidate, and then choose the rank that minimizes the mean of the root mean square error. We can do the same exercise for the P. The one thing that we discovered is using the cross-validation for R outperforms the other the conventional ideas, like for example, using the information criteria, or if you're familiar with the dynamic vector models, then one can just come up with the edge distributions or sort of any other method. But the cross-validation is outperforms the others. So we can also support the theory of the estimation. So there are three sets of the assumptions. So first set of the assumptions is about how much my estimate the autocorrelation matrix are Z hats is away from the true one. Okay. So, and then the pair of the assumptions is about this is the key assumptions of the non-asymptotic the concentration inequality. So about this C1 and C2 assumptions, we gave the auxiliary lemmas there as well. So this will determine the convergence rate of the parameters and the covariance matrix. Okay. So note that this, as you can see here, the assumptions C1 and C2 are like this. So if you see that the differences between the data hat and the data, it converges to with this rate. So this rate might be strange as it is different from the ordinary dynamic vector model rate, which is 1 over 1 over the square root of the t. Um, we uh, we acknowledge that this rate may not be the optimal, but this will give the sufficient rate of the convergence as the t dominates the number of the variables t here. Okay, and the simulation results, and we included in the paper, supports this idea. And then the last set of the assumptions, F1 through the F4, is about the standard dynamic vector models, the assumptions, as like um, the Chamberlain and Rothschild's the vector models, or just Dawes papers are used the same the assumptions as well. So so the two set of the convergence rates here is my estimated the autocorrelation matrix, the RZ hat is with this the discrepancy of the true the vector part is just bounded by with this rate. Okay, so if we just think the first rate as 1 over square root n, this is identical to the rate of the typical dynamic vector models. Okay, so likewise we can do the same exercise for low dimensional the covariance matrix of the vector series y, and we get the same result as this. And for the rest of the estimators, like the transition matrices size and the loadings matrix will have the same the rate of the convergence as well. So in the forecasting, the second chapter of this work is about the forecasting. So forecasting is like given the historical path of the discrete observations, I want to make a best guess of the x after the t steps ahead, and it's like getting the conditional distributions of your estimates. Okay, so if you can come up with how these variables are defined, it's like the marginally beating your xits with the suitable thresholds. So this problem is just simply converged to just transformed into the estimating your zts with where the zts are truncated by the proper the beans. Okay, so for deriving your zts, you're just simply using the Kalman recursions, like a prediction and the filtering operations. And for getting the conditional distribution, which is the conditional expectations like that, then you can just use this simply particle filtering. Okay. And after the last observations, you can use the prediction steps for in the Kalman recursions as well. There are two the hacks that we have to use for the computational feasibility. So one is if you just try to use this V the jointly defined V, the indicator function, then there are very much number of the possibilities that you have to think. Like for example, even if you just come up with if you just try to use the Bernoulli distribution, there are 2 to the d power of the possibilities, but this is not the ideal situation. So just to use the marginally defined indicator function to try to reduce the number of possibilities to be d. And we know that using the Kalman recursions, the forecasting the errors are reflected by the prediction the covariance of the prediction errors are converging quite quick in a few steps. So we can just simply use the last few observations, let's say within the 10, then you can reach the converged the covariance matrix of the forecasting errors. So everything else just is how to get this descent, the generate the path of your Z's. So let me just skip this simulation result. So simulation result is just simply if this model is behaves quite similar to the ordinary dynamic vector models, and then the answer is yes. So data application in this model is about the big so-called the big five personality the data in psychology. So we assume there are five vectors, and each of the vectors driving the six the observations through the nine days. Okay. So as you can see, each of the categories has the the patterns of the six variables for each. So estimation results tells you there are clear block structures, as you can see, and then the low dimensional the estimated bar transition matrix has the non-trivial values. Okay, so we can confirm the vector structures here, and it's driven by the low dimensional the bar models as well. In addition to the estimate result, you can do the model diagnostics by using the so-called PIT. So uh, I don't want to talk about too much details about the PIT, but the rationale here is if you generate, if you once you just get the estimates, and then if you convert into them into um, the PIT, the histogram. So if this the distributions of your histograms gets flat around zero point 0.1, with if you are using the 10 beans, then your the model the fits are very good. So except some of the cases, we are generally have the very good fit model fit. And forecasting part, well, we can come up with the three benchmarks. So one is to just simply use the last observations, and the other is to marginally think. So forget about the vector structures and marginally forecast your observations. And the last one is about forget about the vector structures, but the observations is driven by something non-structured latent process. Let's say the white noise. Okay. So our method here in this case slightly outperformed, but essentially, eventually at the long run, let's say at the 5 step ahead forecast, then everything here is just converged to the same values. So we propose the estimation and the forecasting the framework of the dynamic vector models, latent dynamic vector models, using the so-called Gaussian transformation. So estimation is based on the second order properties, and we are also providing the block cross validation idea for the model selection part. And theoretic part of the consistent result has been established as well. And for the forecasting, we are just introducing the idea of the combining Kalman recursions and fatigue filtering. And the estimations and the forecasting are applied to the various synthetic data sets and data applications in the psychology. So this is all I have. Thank you.